Fine students, in the last class we just started with the EMI chapter, right? So EMI chapter is nothing but, we call EMI, the full form of EMI is nothing but electromagnetic induction. So we shall have a recap of last class for a few minutes. So as you know that in the ancient days they thought that there was no relation between this magnetic field and electric field. So later the scientist called as Oersted discovered that there is a relation between the electric field and magnetic field. Okay, so Oersted discovered that electric current produces magnetic field. He discovered later this Ampere and the other scientists found that even that electricity and magnetism are interrelated. So the scientist Ampere conducted some of the experiments saying that moving electric charges produces magnetic fields. Okay, so this established an relation between electricity and magnetism. Okay, so the phenomenon in which the electric current is generated in closed coils by varying magnetic fields is called electromagnetic induction. Okay, so the phenomenon in which electric current is generated in a closed coil by varying the magnetic field. So whenever there is a change in magnetic field or the magnetic flux across a closed coil, so what happens, there is a induced current in the coil. So we call that as the electromagnetic induction. Okay, so and we also just went through about this three experiments, right? Experiments of Faraday and Henry. So the first experiment was current induced by a magnet, correct? So in this experiment we had a coil, okay, which has some turns, which has been connected to a galvanometer, okay, and we have a magnet, okay, bar magnet, so which has north pole and south pole. So as you know that when you move this bar magnet towards the left, so what happens, the magnetic field, okay, linked with the coil changes. Okay, so what happens due to that, so there is a induced current in the coil. So the galvanometer shows deflection. Let us say it is showing deflection in the left side. So next, what happens when you move the magnet away from the coil, so what happens, again the magnetic field or the magnetic flux linked with the coil varies. So due to this, what happens, again there is a current induced but in the opposite direction. So the galvanometer shows the deflection towards the right now. Okay, so the same observation it is made, okay, when you keep the bar magnet stationary and when you move this coil towards or away from the bar magnet. Okay, so hence it is said to be that one, either the magnet or the coil, it is in relative motion. Okay, when it is in motion, so there is a current induced. Okay, so if you keep both the coil and the magnet stationary, so there is no induced current. Okay, so this was the conclusion by the first experiment, that is current induced by a magnet, right? So next, coming to this experiment 2, it is said that the current induced by current. So as you know that in this case you have two coils, right? You have two coils which has the common axis, right? So one of the coil, that is C1, which has some number of turns, which has been connected to a galvanometer. So the second coil, even it has some of the turns and it has been connected to a battery. Okay, so as you know that since C2 is connected to battery, once the current starts flowing in the circuit, that is in the coil C2. So if you move that coil C2 towards the coil C1, okay, so what happens, there is a change in magnetic flux or magnetic field linked with the coil. Okay, so hence what happens, there is a induced current in the coil. So the galvanometer, let us say it is deflecting towards the left. Now again, if you are moving that C2 away from C1, so what happens, again the direction of induced current will be in opposite, so the galvanometer shows the deflection towards the right. Okay, so this is what you are going to observe. Okay, again the same thing, if you are moving, if you are keeping this coil C2 constant and if you are moving this coil C1 towards or away from the coil C2, so what happens, again there is a induced current in the coil. Okay, so hence we say that whenever either the C2 or C1 is moved towards or away. Either the C2 is moved towards C1 or away from the C1, either the C1 is moved towards the C2 or away from the C2, there is a induced current. Okay, current is induced in the coil. Okay, so that is the experiment regarding the uh, second experiment, that is current induced by the current. Okay, so since the coil C2 has a current, since it has been connected to a battery, so C1 has been not connected to any battery, there is no current, but you are inducing a current in the coil C1 due to change in magnetic flux linked with the coil C1. Okay, so that is regarding the second experiment. Next, coming to this third, you can see that it is regarding current induced by changing current. Okay, current induced by changing current. You can see there again the C1, coil C1 has been connected to galvanometer and the coil C2 has been connected to a battery. Okay, so you have a tapping key there. Okay, the meaning of this tapping key is nothing but whenever you tap this key, okay, when you press this key, there is a momentary deflection. Okay, that means that the current starts to flow. Okay, so the current starts to flow in a step by step. Okay, it increases by step. At some point what happens, the current becomes saturate. Okay, the value of current doesn't increases. Similarly, when you release this tap key, okay, so what happens when you release this tap key, again the current in the circuit decreases by a step by step. Okay, the current decreases in a step by step and it comes to 0. Okay, so this is the uh, use of this tap key here. Okay, so let us say that you are pressing the tapping key now. Okay, you are tapping you have pressed the key there. So what happens, the current is increasing in a step by step. So what happens, since the current is increasing in a step by step, so due to that varying current, what happens, even the magnetic field also varies. So since this varying magnetic field or the varying magnetic flux is linked with the coil C1 which is placed beside to that C2, so what happens, there is a induced current produced in the coil C1. Okay, so next what you are going to do is, since the current increases by step, that is 0.51, 1.52, so what happens, since the current, the value of the magnitude of current is varying, so there is a change in magnetic flux. Okay, so next what happens here is, at some after some time the current becomes saturated in the circuit. So once the current becomes saturated, so what happens, again the magnetic flux or the magnetic field, okay, which is produced due to that current becomes maximum. Okay, I mean it doesn't changes. Okay, the value of magnetic field doesn't changes. So hence the magnetic field or the magnetic flux which is linked with coil C1 also doesn't changes. So the current in the coil C1 is nothing but equal to 0. Okay, so next assume that you have released the tapping key. Okay, so next what happened, the current starts to decrease. Okay, the current starts to decrease in a step by step. Let us say that from 3 to 2.5, from 2.5 to 2, 2 to 1.5, 1.5 to 1, 1 to 0.5, 0.5 to 0. Okay, so what happens there is, again there is a decrease in current. Okay, the value of the current is varying. So since due to that what happens, even the magnetic field value changes. So hence the magnetic flux linked with the coil C1 also changes. So the current is induced in the coil in the opposite direction. So the galvanometer which is connected to the coil C1 shows the deflection in opposite direction. Okay, so hence after some time the current in the circuit, that is C2, becomes 0. So hence also the current in the coil C1 is also 0. Okay, so this is regarding the experiment of current induced by charging, current induced by changing current. So the value of the current keeps on changing. Okay, due to the changing current, the value of magnetic field also changes. So hence the magnetic flux which is linked with the coil C1 also changes. So due to that the current is induced in the coil C1. Okay, so this is regarding the experiment 3, current induced by changing current. So these are the 3 experiments Okay, which are the three experiments of this Faraday and Henry. Okay, so in case if you have any doubts, you can ask regarding these three experiments. Okay, I have just posted these notes in the group, right? I have forwarded these notes in the group. So in case if you have gone through the notes, I mean the topics which we have discussed in the last class. So in case if you have any doubts regarding that, you can get it clarified now. Okay, any doubts regarding the three experiments? Okay, fine. See, what do you mean by this magnetic flux? What do you mean by this magnetic flux? If you remember about this electric flux, it is very easy to define magnetic flux. Okay, what do you mean by this magnetic flux? Anyone? Okay, Jose and Jose, it's the number of magnetic lines passing through a closed surface. Okay, so exactly it is the number of magnetic field lines passing through a given surface. Okay, so more is the magnetic field lines passing through a given surface, we say that more is the magnetic flux. Okay, so magnetic flux is nothing but the number of magnetic field lines, okay, passing through a given surface is called as magnetic flux. Okay, so in the same way we have defined this magnetic flux, okay, as same as that of electric flux. Okay, so in the case of electric flux we have derived that phi is nothing but it is nothing phi subscript e is nothing but it is a electric flux, right? Electric flux is nothing but equal to, we have written that one as vector e dot vector ds, that is nothing but equal to eds cos theta. That was regarding the uh, electric flux, I think, right? E dot s is equal to es cos theta, I think. So in the same way we are going to denote this magnetic flux. So magnetic flux is denoted by phi subscript b, where b denotes the magnetic flux. Okay, that is nothing but equal to vector b dot vector a. So since it is a dot product, it is expressed in terms of cos. So b vector b dot vector b, a is nothing but equal to ba cos theta. So where theta is the angle between the vector b and vector a. Okay, a is the area and b is the magnetic field. So theta is the angle between that two. So as you know that the magnetic flux is maximum when it is normal to the surface. Okay, next, that is nothing but when theta is equal to 0 degree. Similarly, when the magnetic flux is 0, when the field is parallel to the surface, that is when theta is equal to 90 degree, we say that the flux is minimum. Okay, so this is regarding the magnetic flux. Okay, next you have a explanation of that. Okay, so since they don't ask in your examination, so let us don't go beyond that. Okay, so it's a extra information given. Okay, so from here to here just you can go through, okay, by yourself. So next it is regarding 1 Weber. Okay, 1 Weber is nothing but equal to 1 Tesla into 1 meter square. Okay, it helps in when you are solving the numericals, and also when you take some competitive exam like CET, NEET, so it helps there. Okay, the SI units, 1 Weber is equal to 1 Tesla into 1 meter. So now coming to this next, Faraday's law of electromagnetic induction. Okay, so it's Faraday's law of electromagnetic induction. See, coming to this first law of electromagnetic induction, it is said that the statement, whenever the magnetic flux through a circuit changes, an EMF is induced in it. The induced EMF lasts as long as the change in magnetic flux continues. Okay, that is the first statement of Faraday's. Okay, it is the first law of Faraday. So he says that the meaning of that first statement is nothing but, he says that whenever the magnetic flux through a circuit, okay, whenever the magnetic flux through a circuit changes, there will be an induced EMF. Okay, so voltage EMF is almost the same, this is one and the same. Okay, so instead of voltage we call that one as EMF also. So there will be an induced EMF. Okay, even there will be a induced current due to that. So whenever there is a change in magnetic flux, there will be a induced EMF in it. Okay, this induced EMF which is induced in the coil will be there as long as there is a change in magnetic flux linked with the coil. Okay, so once the change in magnetic flux stops, okay, so what happens, the induced EMF in the coil will be nothing but equal to 0. There will be no current. Okay, so that is the meaning of that first law of Faraday. Okay, next, coming to the second law, it is said that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. Okay, it is said that however the magnitude of EMF, I mean the magnitude of induced EMF is directly proportional to the change of magnetic flux linked with the circuit. So if you say that the magnetic flux linked with the coil changes more rapidly, so what happens, the current induced in the coil will be more. Okay, if the rate of change of magnetic flux linked with the coil changes very slowly, okay, if it is very slow, so the induced EMF will be a small one. Okay, hence it is directly proportional. So we are going to define that one by mathematically, we are going to express that one in terms of mathematics. There is nothing but, see here, if the magnetic flux linking a closed loop changes from phi1 to phi2 in a time interval t, the rate of change of magnetic flux is nothing but equal to phi2 minus phi1 divided by t. That is like final minus initial, what you are going to take, like that itself. So the value of magnetic flux changes from phi1 to phi2. So hence the rate of change of magnetic flux is taken as phi2 minus phi1 divided by t. Okay, or you can take, instead of t, you can take there dt. Okay, in the time interval dt. If epsilon is the magnitude, okay, sorry, if E is the magnitude of the induced EMF, according to the Faraday's law, E is directly proportional to phi2 minus phi1 divided by t or dt. Okay, as we have studied it, according to the second law of Faraday's law, it is said that the magnitude of EMF is directly proportional to the change of magnetic flux, right? So hence E is the induced EMF and phi2 minus phi1 is nothing but the change in magnetic flux divided by time. Okay, so hence this is a constant, I mean proportional. We are going to add a constant in the next step. Okay, we are going to add a constant in the next step. So K is a constant, where K is called as the constant of proportionality. Okay, in all the systems the value of K comes out to be as 1. Okay, so hence the value of E comes out to be as E is equal to phi2 minus phi1 divided by t or dt. Okay, so hence that change in magnetic flux, that is d2 phi2 minus phi1, can be expressed as d phi. Okay, the change in magnetic flux, that is phi2 minus phi1, is nothing but what, change in magnetic flux, right? So hence that one we are going to replace that one by E is equal to minus d phi divided by dt. Okay, so this is the mathematical form of Faraday's second law. Okay, so just go through once about this magnetic flux first, then go through about this Faraday's first law and second law. In case if you have any doubts, please let me know. Okay, just go through for a few minutes about this magnetic flux and Faraday's first law and second law. ಸ್ಯಾನಿಟೈಸರ್ ಎತ್ಕೊಂಡು ಹೋಗಂತ. ಇದೆಯಾ ಸ್ಯಾನಿಟೈಸರ್? ಎತ್ಕೊಂಡು ಹೋಗು. ಆದಷ್ಟು ಬಸ್ಸಲ್ಲಿ ಲಾಸ್ಟಲ್ಲಿ ಕುತ್ಕೋ, ಲಾಸ್ಟ್ ಖಾಲಿ ಇರೋ ಕಡೆ ಕುತ್ಕೋ, ಹೋಗಿ ಮುಂದೆ ಅಲ್ಲಿ ಕುತ್ಕೊಬಿಡಲ್ಲ ಹೋಗ್ಬಿಟ್ಟಲ್ಲಿ.
ಸ್ಯಾನಿಟೈಸರ್ ಎಲ್ಲಿದೆ?
Okay, fine. Any doubts, students, regarding magnetic flux and about this Faraday's first law and second law? Any doubts you can ask. Okay, fine. Meghana, no doubt, sir. How about others? How about others? Is it cleared? Have you understood? Okay, fine. Can anyone tell me why is that you have a negative sign here? E is minus d phi divided by dt. Why is that negative sign? So in this case you can see here, in the previous step you don't have any negative sign there, right? But in the final expression we have written negative sign there. What does it mean? What does that indicate? Yes, anyone? Why is that negative sign? How come it came at the last? What is the significance of that? Yes, Meghana, Josen, Pratik, Shajit. Okay, fine. See here, that negative sign is taken because the induced EMF always opposes any change in magnetic flux associated with the circuit. This follows from the Lenz's law. Okay, so see here, that negative sign indicates that always the induced EMF, the EMF it is induced in the coil, due to the change in magnetic flux. Okay, so that induced EMF always opposes the change in magnetic flux linked with the coil. As you know that only when there is a change in magnetic flux linked with the coil, there will be an EMF induced in the coil. Okay, but that induced EMF always opposes the change of magnetic flux linked with the coil. Okay, hence we have taken E is equal to minus of d phi by dt. E is nothing but what? EMF. D phi by dt is nothing but change of flux with respect to time. Okay, so since EMF opposes, it is taken as negative there. E is equal to minus of d phi by dt. Okay, so this follows the Lenz law. Let us see what is that Lenz law. Okay, before that, in the case of a closely wound coil of n turns, the change in magnetic flux associated with each turn is the same. Therefore, the total EMF induced is given by E is equal to minus n d phi by dt. Okay, as you know that, let us say that you have n number of turns. Okay, you have taken a coil which has n turns. Okay, so if that is the case, what happens? The magnetic flux associated with each turn remains the same. Okay, the change in magnetic flux associated with each turn remains the same. So hence you can write the total induced EMF as E is equal to minus n d phi by dt. Okay, so it is in the last line, it is said that by increasing the number of turns in the coil, we can increase the induced EMF. Obviously, if you increase the number of turns, the EMF induced will be more. Okay, so this is regarding that second law of Faraday's law. Okay, that is when you have more than one number of turns. Okay, so where n denotes n number of turns, where you can write n is equal to, can take the value from 1 up to n. Okay, so next it is regarding Lenz law. Okay, so let us see what is this Lenz law first of all. Okay, in 1834, German physicist Heinrich Friedrich Lenz deduced a rule known as Lenz law, which gives the polarity of the induced EMF clearly and precisely. Okay, so as we know that till now we studied that whenever there is a change in magnetic flux linked with the coil, there will be an induced EMF, right? But we didn't worry about the direction of that induced EMF, right? We didn't go through about that direction. Just only we make sure that whenever there is a change in magnetic flux linked with the coil, there will be an EMF induced. That's it, right? So now this Lenz, okay, the scientist, the German physicist gave the polarity, okay, polarity of this induced EMF. Okay, so let us see that the statement of this Lenz law. The polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Okay, once again I will read out. The polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux. Okay, so that is the statement. So now this Lenz law is regarding the conservation of energy. Okay, this Lenz law is according to the conservation of energy. So let us see how it is related to this conservation of energy. So I'll just read out the first paragraph, that is about figure A, that is about the first figure. So see here, when the north pole of a bar magnet is moved towards a coil, the direction of induced current is in anti-clockwise, is such that the near face of the coil acquires north polarity. Therefore, work must be done against the force of repulsion to bring the magnet closer to the coil. Okay, see here, let us say that you have a coil here. Okay, so as you know that, let us say that you have a bar magnet. This is north pole and this is south pole. Okay, let us say that you are moving this bar magnet towards the coil, that is towards the left. So what happens, what Lenz says it, the direction of current induced in the coil due to the change in flux, it will be in anti-clockwise direction. It says that the direction of induced current will be in the form of anti-clockwise direction, and the coil, okay, the coil acquires the polarity of north, okay, the phase of the coil, you can see the phase of the coil, okay, the phase of the coil acquires the north polarity, okay. That means that since it is in anti-clockwise direction, the induced current, you can write that one as like this, okay. So it represents the direction of induced current. So hence it is said that it acquires the phase of the north, it acquires the north polarity, the coil. So hence, since you can see there, you are moving the north pole of the magnet towards the coil. So what happens, since even this is a north pole and even this acquires the polarity of north, what happens, there is a force of repulsion, okay. So in order to move this bar magnet towards the coil, what happens, you need to do some work, okay, in order to overcome that repulsion, okay. That is the first case, fine. So next case, that is the second one. Again you are going to take a coil, okay. Next what you are going to do is you are going to take a bar magnet, okay. Now what you are going to do is north pole, south pole, okay. Let us say that when you are moving this coil away from the, when you are moving this magnet away from the coil, so what happens, the current induced in the coil will be in the, will be in a clockwise direction, okay. So hence this coil acquires a polarity of south pole, okay, it acquires a polarity of south pole. So direction of anti-clockwise is like this, right, the same thing we have written here, it acquires as the polarity of south pole. So what happens, as you are moving away the coil, away the bar magnet from, I mean as you are moving the magnet away from the coil, what happens, so this coil acquires a polarity of south. So hence what happens, it exerts a force of attraction, since it is a south pole and this is a north pole. So hence in order to move the coil, in order to move the magnet away from the coil, you need to do the work done against the force of attraction, okay. So in the previous case you need to do the work done to overcome that force of repulsion. So in this case you need to exert a, I mean to do a work done against the force of attraction, okay. So hence in both the cases we say that there should be a some work done. So hence we say that that energy what you are doing, okay, will be converted in a form of electric energy, okay. So whatever the work you are going to do will be converted into electrical energy, and that itself appears as a induced EMF in the coil, okay. So hence this Lenz's law is according to the law of conservation of energy, okay. And this is about the Lenz's law, okay. So in your examination they are going to ask this Faraday's law, either they can ask first law or second law, either they can ask about this Lenz's law, okay. Just go through about this, they don't ask about the explanation of this, okay, how did this coil took north polarity, how this coil acquires the south polarity, that and all they don't ask. They are going to ask about this statement of the Lenz's law, and the Lenz's law is according to, in accordance to what type of conservation they are going to ask, okay. So this is regarding the Lenz's law, okay. Just go through, in case any doubts you can let me, okay. Okay, fine. Any doubts, students? Okay, fine, students. So just go through the topics which we have discussed today. Okay, in case if you have any doubts, please let me know in the next class. So with this thing, I'm just concluding today's class. Okay, thank you.